We're going to hear from Patrick Reddy, who's a retired chief forecast and research meteorologist, and also at the Colorado Department of Public Health. He served as the chief forecast and research meteorologist for the Colorado Department of Public Health and Environment until he retired this fall. He played a lead role for Colorado in the planning and implementation of the NCAR FRAP and the NASA Discover Act field campaigns, looking at the photochemistry of Colorado's Front Range in 2014. He's been using satellite air quality data extensively for regulatory and policy analyses. He's worked with scientists from a number of different federal agencies, including NOAA, EPA, NASA, NCAR, to use this satellite air quality data to better deal with air quality issues in the West. He's also been working on sort of satellite monitoring for renewable energy technologies, and he received his bachelor's from St. Louis University, got his master's in biometeorology from the Yale School of Forestry and Environmental Studies.
So I'm going to give you an overview of how Colorado has used satellite air quality data for air quality management issues over the last several years. So Tracy asked me to point out that the degree to which Colorado uses air quality data or satellite data for air quality issues is kind of unusual, and apparently we use it a lot more than other states do. She and an intern of hers, together with me, put together a pretty nice article about how Colorado uses air quality data, and it was in the special issue of EM magazine from 2014, and that's where these graphics are from. That issue covered a lot of the NASA ACAST programs, and it's a pretty good issue to take a look at. So it's my impression that whether or not a state uses satellite air quality data a lot depends, at least for states like Colorado that are kind of small, on whether or not the staff and managers are interested in that approach. There's a pretty steep learning curve. Data sources, tools, and methodologies are new and changing rapidly. I would like to echo what Brian said. A big boost for us happened in 2012 when I started connecting with the NASA ACAST folks, and there's 4 of them here today. I also took one of the NASA RSET training classes, and it was pretty easy and very productive. There are several reasons that Colorado is a good state to use satellite data in, and one of those is that the terrain is very complex and we have diverse sources of air pollution. The terrain tends to segregate the state into distinct air sheds. It's a large state. Monitoring at the surface is expensive and it's hard to cover the whole state. And we have a lot of dust storms, wildfires, and stratospheric intrusions of ozone. Those events lend themselves to using satellite data. We also have a large urban-rural non-attainment area for ozone along the Denver, Boulder, Fort Collins Front Range urban corridor. Excuse me. So here's a list of some of the things we use satellite data for. We prepare climatologies and assessments of terrain effects, and those are used for a variety of these other topics, including siting air quality monitors in new locations, estimation of background nitrogen dioxide concentrations for permit modeling. That's something that's kind of taken off in the last couple of years. So if a new source or a source that's being modified has to do permit modeling and they need a background NO2 concentration, we use OMI NO2 data to get an idea of what that background should be. We have between 5 and 15 stratospheric intrusion events each year, mainly in the spring and early summer. We forecast those events, and the satellite data from today helps us anticipate what's going to happen tomorrow. We also have to flag those events as possible exceptional events in the EPA air database and prepare detailed analyses for those events if we try to request that those events be exempt. Dust storms and wildfire smoke are also good candidates for both using satellite data for forecasting and analyzing those events after the fact. And then we use satellite data to some extent for looking at trends. In the future, with new satellites coming online in the next couple of years, we would expect that we would be able to do more detailed weight of evidence analyses for state implementation plans for ozone, better forecasting. It's likely that models will improve gradually with feedback from satellite data. And with some of the satellites, we should be able to get actually really good data for specific events, the kind of events that SIP modelers look at to try to comply with the standards. So here are a couple examples of looking at how terrain affects air pollution climatology along the Front Range. Excuse me. In these two plots on the left side, you've got the higher terrain of Colorado along the Front Range. On the right side of each plot is the plains and the Front Range urban corridor. There's a river valley that runs from Denver to Greeley, and it's very wide north of Denver, and at night and in the morning, emissions of NO2 from the urban corridor tend to drain into this valley and pool. And that's what we see on the left plot. That's a mean winter plot from the GOM-2 instrument, and that's from a mid-morning overflight. In the summer, by mid-morning, the emissions that pool in the valley north of Denver are already starting to migrate towards the west into the mountains. The mountains tend to heat up in the summer, you get a little area of low pressure, and you've got thermally driven upslope flow that carries emissions and air pollutants into the mountains. So this right plot is a mid-afternoon OMI plot of NO2, and you can see that the NO2 is not in the basin in this case, and it's starting to migrate up into canyons towards the west. There's that finger of higher NO2 you can see just west of Denver. That's pollution migrating up Clear Creek Canyon. We use this information in particular to try to plan where we should be monitoring and flying for the 2 field campaigns that occurred in this area last summer. So we sighted some extra ozone monitors up along that canyon, and were able to conduct a few flights up there as well, and we did find high ozone in that region. So with increased oil and gas development in the state, we have some areas that are expected to have more oil and gas wells in the future. One of those is in Paradox Basin. This is in the Four Corners area of southwest Colorado. And under the Paradox Basin label there, you can see a stippling pattern. That's where the proposed oil and gas wells would go in. The black dots are existing oil and gas wells in the San Juan Basin in northwest New Mexico, and that's an area of lower terrain. There's a lot of NOx emissions associated with those facilities, and also one of the largest emitters of NO2 in North America, power plant right in that area. So the blue color there actually indicates that NO2 is high, and it follows the basin. Ozone monitors, the red triangles represent ozone monitoring sites. The ones that are in the oil and gas fields and in that blue area tend to have lower ozone concentrations, probably because there's too much NOx, and there's 2 ways that can happen. But anyway, we wanted to site a monitor that we thought would be really good for estimating the impacts of the Paradox Basin development area and not seeing reduced ozone because of that high NOx concentration in the San Juan Basin. The monitors were actually sited kind of above where the Paradox Basin label is shown there. So as Brian mentioned, you can use indicator ratios from space. The ratio from aldehyde to NO2 to kind of estimate how sensitive ozone is to NOx reductions. And I used his method back in 2009 to calculate those ratios for Colorado. And the motivation for this was that at the time, one of the commissioners who was an atmospheric chemist, and another atmospheric chemist in the area, and a lot of folks from industry were saying that really NOx reductions in Colorado would be detrimental. And if you reduced NOx, ozone would go up. So this, to me, seemed like a great opportunity to provide a good way to counter that argument. All these ratios are above 1, which tends to suggest that in all those grid cells, you would likely have some benefit, some reductions in ozone by reducing NOx. That may not be true. If you look at the lower left corner, you can see the pink values there. That's back in that San Juan Basin where the major power plant is, and the emissions from the oil and gas fields tend to pool in that basin. So I looked at that same issue another way using OMI data for 2005 through 2013 and ozone data. Both NO2 and ozone tend to go up when high pressures are present. They correlate really strongly with weather. So I took that effect out, and so I've got weather-corrected ozone and NO2, and I just looked at the correlation coefficients between those two weather-corrected data sets. And so you can see that the correlations are highest along the foothills west of Denver, and those happen to be also our highest ozone concentration sites. So this again suggests that this is generally a NOx-limited area, and reductions in NOx would be beneficial. So as I said earlier, we have a number of stratospheric intrusions of ozone in Colorado. It tends to be worse during La Nina years, and we're having an El Nino year this year, so we may not have many next spring, next June. But with a new lower standard, there are a couple areas in the state, Colorado Springs being one of them, where we may exceed the thresholds for attainment of the standard. And so I'm going to show an event from 2010, and the standard at Colorado Springs, which is south of Denver, was exceeded on this day. And in the left panel, I've plotted a meteorological tracer for stratospheric air. It's called Isentropic potential vorticity, and it's a nice conservative tracer. And the values are high over central Colorado for that day, and the numbers are probably too small for you to see, but concentrations of ozone range from about 85 to 98, where those values are high. So that's a good indication, among many others, that those high concentrations of ozone were caused by an intrusion event. The problem with these spring intrusion events is that often you bring in air pollution from China at the same time, and it may be on the flanks of the low pressure system. Brad could explain this better than I do, but there's usually a broad swath or often a broad swath of Asian springtime transport air pollution somewhere in the vicinity of these springtime lows. So one way to kind of eliminate that as a possible contributor to the high ozone is to look at AIR's satellite carbon monoxide concentrations. Carbon monoxide is really low in the stratosphere, and so in this right plot we see with the blue pixels low concentrations of carbon monoxide over the area that had the high ozone. So that's a kind of extra evidence that this event was stratospheric in origin. It was not mixed with Asian ozone, which can be a problem, and a lot of events it's not so clear cut. And that's why we're glad that we have modelers. And here's a plot of a model output from Brad Pierce. It's with the Real-Time Air Quality Modeling System, or RACMS. And this was for another intrusion event, same time of year in 2012, and the intrusion occurred over central Colorado. Rackham's predicted concentrations above 75 parts per billion, this sort of yellow area over the state, and the actual concentrations were in that ballpark. And his model and other models can tell you or estimate whether that was stratospheric in origin or from Asian transport or transport from California. He and his group developed a ozone forward trajectory tool, and that's been really useful for us. It's based on satellite data, and it uses yesterday's satellite data to project what's going to happen in the coming days, and it's a great tool. It's a great tool for forecasting, but it's also good for documenting these events in case you have to seek exemption through an exceptional event process. In 2012, we had between 40 and 50 dust storms in Colorado that caused exceedances of the PM10 standard. Each one of those had to be documented, and fortunately, I didn't have to do any of them. My coworker there, I trained him, and he spent all year doing it, and each event took up about 20 pages of analysis. But one of the things I learned how to use with the RSIT class is the NASA Worldview site, and I would recommend, if you just Google NASA Worldview, you can find that. It's a great sort of satellite GIS tool, and you can see Aqua and Terra MODIS images, and then various other satellite data, and superimpose those data on the MODIS image. And here's an example of a Four Corners area dust storm. So where it says blowing dust obvious here, that's right at the Four Corners area. The dust storm caused exceedances beyond that region, and I've circled the area where we had an exceedance. You can't actually see the dust very well in the visible image, but if you use the NASA dust score, which is available on the Worldview site, you can see that there is indeed blowing dust there, and this was part of the package, one of the graphs that was submitted in the package that we submitted to the EPA for that event. And I also wanted to mention that every spring I used to go through all the events, find particular ozone exceedance events from the previous year, and determine which ones to flag as possible exceptional events. You flag them, submit the data to the EPA. If you flag them, then you have the opportunity to document or prove that they were exceptional events. If you don't flag them, then you're out of luck. But I use that NASA Worldview site every spring to look at virtually every day during the spring for intrusions. I looked at other things as well, but you can see smoke from smoke events, dust from dust storms. It's really a nice site. So in terms of assessing trends, we've already seen in this session and the other session on ozone earlier that OMI NO2 is a great tool for looking at trends in emissions. I presented this really simplified graphic to the Air Quality Control Commission in Colorado a number of years ago to give them an idea of how emissions had changed between 2008 and 2009. And the recession in 2008 and 2009 really caused reductions in NO2. You can see that in this map. And that was a partial explanation for why we had lower ozone that summer. So this is one of the main issues of this session, global and regional background in transport. That's a really complicated issue, and probably better tackled by many of the other folks here today. I would like to refer people who would like to delve into this, into the conference proceedings from a transboundary ozone pollution conference that was held in Yosemite earlier this year, so the link is there if you want to check it out. One of the key things I think for state air quality managers is relying on the research community and research grade models to estimate what transboundary the transboundary component is and what background is. And included in this research community are NOAA, NESDIS, NCAR, NASA, Columbia, NOAA, GFDL, Harvard, NASA ACAST, and many others. A lot of the global models assimilate satellite data now, which improves their performance, or at least it should improve their performance. And these include Rackham's GEOS 5 and 6, CamChem, which replaces Mozart, and others. I wanted to end with a slide about Tempo. So Tempo is supposed to be launched, what, in 3 years, maybe? And it is going to be a high-resolution geostationary satellite measuring with a pixel resolution of about 2 by 4.5 kilometers, I think at this latitude. In 2014, during those field campaigns, NASA and Ball Aerospace flew the prototype instrument for the Tempo mission on a jet, and they scanned the Front Range. So this plot here is my attempt to give you an idea of what the resolution would look like. That flight, actually it might have been 2 flights, but this spans several hours, so it's not an hourly snapshot or hourly average. But what I wanted to point out is that it actually shows small and medium-sized power plants along the Front Range. If you're able to see that kind of information every hour on a clear day, I think that's hugely powerful. Tempo will measure other species, and I think it will greatly enhance air quality managers' abilities to forecast. It should improve modeling and model verification, and it should be a great thing. And that's all I have. Thank you.